Exercise 41.18. The exercise is to be solved with the assistance of the TI-Nspire CX CAS version 3.2. Consider the region that lies to the focus side of the parabola, whose equation is y equals to 275 over 1248x squared minus 275 over 78x plus 727 over 130. And interior to the ellipse, whose equation is x squared plus 4y squared minus 16 equals 0. Part A, provide a graph of the region. Part B, provide a graphic approximation of the area of the region. Part C, provide a calculus calculation which yields a decimal approximation, 5 significant digits, of the area of the region. Part D, assess the correctness of parts B and C by examining for consistency between the two results. Part E, if able, obtain an exact value for the area of the region. Part A, provide a graph of the region. Alright, I'd like the first page to be a solution summary. So, begin by opening a notes application and titling it. Also, would like the title here to be bold. So, come up here, context menu, format text, bold. And that looks like the largest font possible without having to wrap to a new line. So let's keep that. Okay, and for part A, we can point out to the reader that a graph of the enclosed region is on page 2, where we will open up a graph application. Alright, so let's open up a second page now. So that's Control, Add Page, and a graphs application. Okay, as we look over at the equations given to us, the first one with the y equals 2 all in terms of x, okay, that's very well suited to go in as a function on the graph entry box, which is what it opens to by default. So we're ready to write it here. Okay, and then hitting enter. Alright, now that's just a little portion of this parabola. Alright, well, we'll wait till we see what the second graph looks like before we decide how much to zoom out and so forth. Just one thing, I suppose, right away, and that is just to keep this graph labeled the same format as the question. We could go here and change the attributes a little bit here. And let's see, first of all, line weight is thin. Actually, let's bump that up a notch to a medium weight. Might look a little better to contrast with the coordinate axes. Okay, a continuous line style, that's good. The label style, here's what we were talking about. Let's scroll over here. That's a y equal to f of x, not that. Here, a y equals to, just like the way the problem states it. Let's choose that one. And scrolling down one more, graph is continuous, of course, that's what we want, and hit enter to lock in all that. Now we have a y equals to equation, just like the question poses. Let's move on to the second equation here. Since it's an ellipse and the equation is provided there, now that happens to be in general form. Alright, well, the fact that it's an equation to begin with means we need to not use a function format. We need to go to the equation format in the graph entry line. So for that, menu and graph entry, and let's choose equation. Now, since it's an ellipse, it might be tempting to look at ellipse here, but you notice the only format provided for an ellipse is a standard form, whereas we have general form. It would not be hard to rewrite this in standard form, but let's not even take any chances of doing any tinkering, and let's instead look at the conic section, and we have it here in general form, waiting for the coefficients. So let's put in what we've got. Our equation specifically has a 1x squared, 1, tab. We have 0xy's, 0, tab. We have 4y squares, 4, tab. We have no x's, 0, tab. 0y's, and a negative 16 constant there. Negative 16, and enter. Okay, there's the ellipse that was referred to. Now, one thing we see, and that is these graphs each have the same color. That's not too desirable. Let's do a little work on this graph of this ellipse here. So what we can do is context menu, go to color, go to line color. Let's pick red for that. Alright, that looks a lot better. Oh, something else. We should change it so that it has a medium line thickness to be like our parabola. So context menu, attributes, and the line weight is now medium. That's the only change I believe we want. Continuous lifestyle, line style. Graph is continuous, and the label prefix, no, we don't want this labeled as E1 or E2, so we leave that alone and just hit enter. Now we can start deciding how to touch things up. Well, first of all, do we see the described region right now? Yes, we do. We can see that this parabola here, just with this much, this is the focus side right here, right? And so then we also need to be interior to the ellipse, so we're inside here. That's our region. Okay, I think there's two kinds of graphs that might look nice. One, rather zoomed in closely, and two, a more zoomed out view that shows us the parabola, and even the focus would look kind of nice in the big picture. So let's get started by first of all zooming in a bit and taking care of the close-up version where we can also do our shading. So for that, let's go to the menu and let's go to Windows Zoom, and I like the zoom box to really control what happens next, and I want to get the described region, and I like the coordinate axes as well. So I'll start the box here with its first corner out to, let's say, and I also want room for labeling, so I'm going to leave a bit of margin around things, I suppose. Maybe there. Let's see if that works. Okay, this seems to have enough room. I'll escape, put that tool away. Had this been a parabola in a circle, I would really go to a big effort to make the axes scaled the same. Do a zoom square so the circle, it indeed looks like a circle. However, since it's an ellipse, I'm not too concerned about distorting that a little bit. It looks like an ellipse almost regardless of how distorted it is by having axes scaled differently. So I'll let that go. However, the axes are a little bit clumsy looking right now. I want to clean them up with simple numbers on the lengths as well as simple tick marks. So I'll go take care of that right now, and that's a matter of going menu, Windows Zoom, the Windows settings. Okay, simple numbers such as a -1, tab, make that a 5, tab, 1 apiece on the axis will look fine, tab, a ymin -3, tab, ymax, call it 3, tab, scaling at 1, tab, and enter. Okay, that looks a lot nicer, I think. Now let's see, let's put these things like this equation out of the way. Okay, pretty good there. So next we might get the points of intersection here. They're going to be important for further discussion. So let's go to the menu and geometry, and points and lines, intersection points. Okay, we need to just click on the two curves we desire intersections for. We only have two curves, so the red one, click, and the blue one, click. Okay, there we have some intersection points. Those do not have a whole lot of decimal places in them as they're written, so I think I will not bother to change the settings on this to trim that down any further. This is not too complicated looking. Let me just put them in nicer locations. So I do have to first escape this tool before I can move these around. Now I can move them, and I think I'll put this about here. I want to make sure that decimal place is still apparent, so I don't want to put the decimal point on the axes. And this one maybe about there. Okay, progress. Now we need to shade the enclosed region, so for that we can draw a polygon and shade the polygon. Menu, geometry, shapes, polygon. So starting here, and I want this to be a fairly accurate polygon because I'm going to use it as a source of graphic approximation of the area as well as a device to shade. Okay, polygon's complete. Escape the tool. Now, context menu and coloring, fill color, go with yellow. Okay, now at this point there's a bit of a fork in the road. I want to use this graph as a graph of the region, and I also want to have a graphic approximation for area. So for one graph I want this polygon, and for the other graph I do not want to be seeing a polygon and its vertices like this. So it's time to make a copy of this and then go in two different directions. So let's go with Control, Show Pages, and here we'll context menu, copy, and context menu, and paste. Okay, this one, page 2, is going to be the graph of the enclosed region. So let's reopen this one, and now let's think about what we'd like to see for the big picture graph of the region. Okay, for one thing, we don't want to see all the vertices of this polygon, nor do we want to see its sides as well. So let's go back here to this polygon and context menu, and let's color those lines yellow as the interior, effectively hiding them. Okay, and now we can go to the points and hide all those except for the intersection points. Alright, looking better. Now the other thing is this question has us getting a region that's supposed to be to the focus side of the parabola. Well, right now it's not so obvious where this parabola is and where its focus is. So to make that a little more obvious, it might be a nice idea to actually zoom out a bit here and really show that parabola and maybe even provide its focus, which we can, as we will see, it is very little effort. So first let's zoom out a bit here. So Windows Zoom, zooming out. Let's try there. Okay, starting to see this parabola one more time. Alright, there, that will really do it. Here, let's escape this tool and let's maybe refix up some of the things that were on our graph. First of all, these coordinate axes now have these rather clumsy end numbers and are now scaled rather densely, so we could change that a little bit. Do that first. Menu, Windows Zoom, Windows Settings. Okay, we'll just make that a -7, Tab. 17, tab. Let's scale every 4. Tab, Y min, negative 12. Tab, Y max, okay, 11. Tab, scaling, I'll make it 4 like the x-axis, I suppose. Okay, that looks a bit simpler. Move these intersection point coordinates near the points themselves. This equation should be near the ellipse. This equation, there's a little more room for it here. Now we could point out that the shaded yellow is the enclosed region, so a little bit of text here. Alright, there we are. Enclosed region is shaded yellow. And the other item that might be a nice touch would be to putting the focus on here so that you can emphasize the fact that we do have ourselves on the focus side of this parabola. And that's pretty easy to do. What you can do is come here to the graph, context menu, analyze the graph, analyze conics, and focus. Okay. Well, okay, it's specific coordinates. Those are maybe a little bit complicated, so maybe we can just kind of hide this and maybe label the focus here as something more simple, like just a letter F might be sufficient. So a little bit of text here, an F. So this looks like a fairly nice graph of the region. Let's go ahead and work on that graphic approximation of the area. Part B. Provide a graphic approximation of the area of the region. Go into our page 3. Here's our polygon. We now very much want to make use of it. So for this, we can come here and go to measurement and its area. Okay. Move this inside and let's make a complete sentence here. Okay, wait a minute. Now the idea of having so many decimal places is starting to haunt us a bit here. We don't want a graphic approximation with 5 significant digits shown. That looks a bit much. So I suppose it is actually time to go ahead and go to our menu and the settings. And for this graphs and geometry settings anyway, let's trim this down to floating 2. Okay. That's more like it for a graphic approximation. Let's also put a little text in here to clearly note what this is. Okay, very nice. Now let's record this result on our summary page. So 5.6 square units. Okay, let's go back to that. And we'll also describe our method of this graphic approximation. Alright, so a polygon can be used as a source of graphic approximation of the area. The result is about 5.6 square units. See page 3. Okay, again, that refers the reader to the source document if they're interested. Part C. Provide a calculus calculation which yields a decimal approximation, 5 significant digits, of the area of the region. Let's decide on a calculus strategy. The most popular strategy is to slice up the region with thin vertical rectangles and sum up their areas. Let's try that out first and see what we think. Looks like 2 obstacles here. When we first examine the tops of the rectangles, things look pretty good. The top of each rectangle is determined by the red curve. Now, when we start to examine the bottoms of the rectangles, things start off with the bottoms determined by the blue curve. But then there's a change. The bottoms of the rectangles get determined by the red curve. That's going to cause us to have to formulate 2 separate integrals to achieve the result. Another issue is that that red curve is determining the bottoms of the rectangles, and it was also determining the tops of the rectangles. That's surmountable. We could use the symmetry of the ellipse here and just use the rectangles down to the x-axis and double the result. However, we should consider some thin horizontal rectangles to see if an easier strategy exists. Let's try slicing again, this time using thin horizontal rectangles. This looks really good. If we watch the right-hand ends of the rectangles, in each case the right end is determined by the red curve. If we watch the left ends of the rectangles, in each case it's determined by the blue curve. So let's next try to informally formulate the area of one of these thin horizontal rectangles. As with all rectangles, the area will be length by width. Here, the length of the rectangle will be its x-coordinate of the right end minus its x-coordinate of the left end. Then its width will be a little section of the y-axis we'll call dy. Let's begin by informing the reader what we have in mind here on the notes page with our solution summary. So a calculus calculation of area can be obtained by using an integral that sums thin horizontal rectangles. Now, how do we begin this? Alright, first we're going to need equations for our x right and x left curves. So let's point that out here, and then we'll need to go to a calculator application to resolve them. Okay, so equations for x right and x left curves are obtained on page 4. Let's take a look at what we've got coming up here. Alright, so as we had pointed out earlier, that x right we're now seeing is a curve which is going to be the right half of this ellipse. Let's first work on that. Now, to work on that, let's, while we're here, grab the equation of that ellipse, and for that it's probably best to perhaps hit tab and scroll up. Alright, here it is here. Control A selects everything and Control C copies everything. Now let's open a page 4. So Control, add page, add calculator. We could say here solve, Control V there, and we want this solved for x, so comma x, and then enter. Alright, we expect to see each equation represent a half ellipse, and that's the case here. Okay, if you find yourself unable to ascertain the basic shape of these x equal to f of y relations, you may want to consider clicking on the link there and going to a 25-minute segment concerning the study of y equal to the square root of a linear expression in x and the graph of a y equal to square root of a quadratic expression in x. If you have the idea of assessing their graph shapes instantly, then these inverse situations that we're encountering here will come easily for you. So it's up to you. It's offered there. If you want to get a better grip on this, if you haven't already, then take a look at it. Otherwise, let's proceed. Now, which one do we want? Let's go back and look again. Of these two half ellipses, we want the one that has the positive x's, right? Now this ellipse is centered at 0, 0, and so its right half has all the positive x's. What's that mean? Let's see, this first one, x equals this positive radical. This other one has got x equal to a negative quantity. Radicals here always have to be positive, so negative 2 times this must necessarily be negative. So here's what we want. Now let's carefully grab it here. So I come here and I go shift and arrow right to select just that expression. Now enter to paste it onto this new line. And now let's go with control store to, and we'll call this the x right of y function. So x underscore right of y. Enter. That's done. Okay, now let's look at our other idea here. We're going to need to get the x left curve. That is the left part of this parabola. If we solve this parabola equation for x, we should be seeing two semi-parabolas, each of which having a vertical axis of symmetry. And what about those semi-parabolas? Okay, well, the terminal points of each will be at the vertex of this parabola. So we might actually spend a moment here. Let's select this graph. Go to the context menu, analyze graph, analyze conics, and let's get the vertex of this parabola on here so we can have something to think about when we look at these two. Now I'm going to delete this later on, but just before we go back to our solving, we realize that the vertex has an x coordinate of 8. So we're going to be seeking the semi-parabola that basically has a x coordinates to the left of 8, right? Okay, so again, we want the semi-parabola whose values, x's, are to the left of 8. Well, we are going to first need that function. So let's go tab to pull up this menu. Okay, it's giving us the equation format. We want the function format. So menu, graph entry, function formats. That's where we had this input, and it's here in this F1. I will now go Control A to select all of this and Control C to copy this. Now go to page 4, and it's another solve, parenthesis. Okay, here's our chance to go Control V to put this in here. Now right now it's got this f of x, f1 of x equals 2. We don't want that. We want it to say y equals 2. So delete that. Put a y. Okay. And now we want this solved for x. So it's a comma, x, and enter. Okay. We are expecting a couple of semi-parabolas. And we've talked about this kind of thing before. The first equation here, indeed it's a semi-parabola, although there's a lot of constants making it look confusing. The essence of this is semi-parabola. How do we know? We see that radical with a linear radicand. Now, while this one here is in sight, let's see what we have to say about it. It's got this 4 times this parenthetical quantity. Alright, let's see here. Down here in this denominator is 275. Now, if we were to split up this radical plus 550, that would be a radical over 275 plus, alright, 550 happens to be 2 times 275, so that's really a plus 2 here. If it's times 4, that's the 8. Alright, there's that 8 we were talking about. So this equation is going to take the number 8 and add to it radical expression, which means it's going to take us to that right semi-parabola. We don't want this one. Okay, so let's go over here and look at the other choice. It's a very similar situation. There's that divide by 275 here. Now this minus 550 happens to get divided evenly by 275 to be this is a minus 2. So when this negative 4 distributes across these two terms here, it ends up with a negative radical and then a plus 8. Okay, this is the one we're looking for then. This is giving us x's are to the left of the number 8. So here's what we want to be selecting. Start here, shift, come over here, there, and then enter to paste it on this line. And now we will go with the control store to, and now we have the x underscore left of y, and enter. Okay, good progress there. Well, we're almost there. What else do we need? We need limits of integration. Okay, well, for decimal approximation purposes, those are very quick and easy to get. Go back to the graph of the region here, and with these thin horizontal rectangles, we have the dy width, which means y is the variable of integration, and so we need to think about what y is doing when we go from the lowest rectangle to the highest rectangle. And so here we want this number here to be our lower limit of integration. Now it's sitting here as a negative 1.6, but we know that's because we have chosen to have two digits displayed. We can get the Nspire to use many of its digits, like 15 of them or whatever, by going with a selection here and a context menu and a store. Now myself, when I'm doing limits of integration with a dy, instead of a to b, I tend to go c to d, just to remind myself that things are a little different in this situation. And I don't want to use just single c, because that's using a single letter for a variable, not recommended for Nspire usage. So I would go a C1, and since this is a decimal approximation, I'll suffix it with an A as well, and enter. Okay, up here is the upper limit of integration. I've got the text selected, context menu, store, and now analogous to be the other one, I'll go D1 and then A, because it's going to be a decimal approximation, and enter. Okay, I think it's time to inform the reader of what we've done for limits of integration and perform the integration. And for that, let's go back to our notes page, page 1. By the way, to quickly go to the end of your document, you can go Control 1, as I just did now, to get to the end of it. So now we're here, and I'm going to also point out that the limits of integration have been stored in variables C1A and D1A. We are now ready to go ahead and compute our area approximation here. Go to the menu and Calculation, Calculus, Integral. All right, here's where we put our lower limit of integration. That's our C1A tab. Our upper limit of integration, D1A tab. For the integrand, we want the x right of y minus x left of y. Rather than all keystrokes, let's just go to this variables menu and take our x right of y minus, back to that variables menu, x left of y. Forward arrow, dy. Okay, go. All right, very nice. Let's backspace here and tack on the square units. Now, that number there, 5.73421, okay, it's too many significant digits. All right, to change the digits here, we'll need to change the digits in the document settings. Okay, so this is not the same as in our graph when we changed the settings for graphs and geometry. We now need to change the document digits. So for that, we go to the document and settings, document settings. We want to float 5. Okay. There, and our new decimal number here has now got 5 significant digits. That's what we want. For this math attribute box, I want to change that little triangle to be an approximately equals to. Okay, there we are. Let's see how that compares to our graphic approximation. Part D. Assess the correctness of parts B and C by examining for consistency between the two results. Alright, to assess the correctness, well, first let's go back and see what we said about the graphic approximation. We said it was 5.6 square units there. Alright, let's make another note of that. And our calculus calculation is still in plain sight, but let's give it a direct mentioning here. Okay, this is good news. If we take the larger number as the basis for percentages, we could say a 10% difference would be about 0.57. The actual difference here is about 0.13. So much better than 10%. If there's no exaggeration in us saying that these two results are within 5% and thus consistent, therefore we believe that the answers are very likely correct. Okay, about like so. Alright, ready to attempt an exact calculation. Part E. If able, obtain an exact value for the area of the region. Alright, an exact calculation has 2 hurdles to be crossed. One is we have to be able to obtain exact limits of integration. Alright, so what does that mean for us? Let's look at this page 2. Okay, we have those approximate limits of integration there, the negative 1.6 and the 1.9, which we actually have to like 14 decimal places by storing those. But from here we see that to obtain them exactly, we will need to get algebraically exact intersections of our x right and x left curves. So let's go ahead and try that on our page 4, our calculator page. Alright, here we are. And something else you can do to help make your document more understandable, you can put in comments here. And to do that, you can go to Menu, Actions, and 6, Insert Comment. Alright, so here we could say that here we attempt to find exact limits of integration. Alright, and now to actually do that, it's another solve situation. And this time we want to see our x right of y equal to our x left of y. We can go to variables, x right of y, arrow forward equal to variables menu, x left of y, arrow forward, and a comma, and we are interested in the solving for, of course, the variable y. And cross your fingers, enter. Oh, okay. Exact is available. We've done that. Okay, now let's grab these and store them. Now these are reported, of course, in ascending order. So here's our lower limit of integration here, exact. So shift, arrow, and enter to paste it here. And now we want to store this into C1. not C1A, which was an approximation. C1, as this is an exact lower limit of integration. So Control, store to C1, enter. Alright, and back up to the second number, shift arrow over to select it, enter, paste it onto the next new line here, and then as before, Control, store to. This will go into D1, no longer D1A. This is exact. Enter. Okay, so let's bring the reader up to date on our success here, and then attempt the second hurdle on the notes page, which is the integral evaluation again. Okay, so as we tell the reader here, for an exact calculation, we first need exact limits of integration. These have been successfully calculated and stored into C1 and D1. And we should also point out, want to see details? Okay, see page 4. Okay, now we'll attempt the integral. See if we can get this to work. So we can first type area equals 2. Alright, one way to calculate this new integral without too much keystrokes is to perhaps go back to this version, go out to say here, I'm going to shift, select to the left. Okay, got that. Now Control C, which copies this integral, and now I will go and Control 1 to return to the end of this document. I'll go with Control V to paste this here. Now this just needs a little bit of editing, really. It's those limits of integration that are no longer approximate but exact. So D1A, now it's a D1. C1A, now it's C1. Okay, let's see what happens. Enter. Oh, it did it. Okay, we got an exact area. Make this look nice. Math attribute box. That little arrow should be a solid equals 2. Okay there. Let's go back here, backspace for a minute, and we can even put on the square units touch there. Now, we've got this, but we're maybe a little concerned that is this right? A little bit complicated looking here. So what is it numerically? Let's find out, and we'll point it out to the reader. We'll go ahead and say here that for extra peace of mind, we will note that and we'll compute the decimal approximation of this quantity. Okay, here's where to do this decimal approximation, I could go back here and shift select this quantity. Okay, Control C to copy it, Control 1 to go to the end of my document, and Control V to paste it here. And now if I do a context menu for actions, I can approximate. Okay, and get this number here, which, if you would recall, this, or you can, of course, we can look back here. Let's look back here for a minute. Yeah, that calculus calculation, that was 5.7342, and we're sitting here with the very same quantity here. So then we can, first of all, fix this up a little bit. Math attribute, that should be approximate equals 2. And then here we can point out with some text, which is consistent with part C. Okay, that gives us an exact solution which matches our calculus decimal approximation, and the overall solution really seems very likely correct because of the consistency we got between our analytic calculation and our graphic approximation. Okay, good job. We're done.